look out for the admitting any continuous stragglers, I suppose. That would be helpful. Otherwise, I'm going to go ahead and introduce Adele. So it is my absolute most wonderful, greatest pleasure to introduce Dr. Adele Morrison. Adele is currently a research fellow at the Australian National University in Canberra. She's broadly interested in understanding the large-scale ocean circulation and its impact on climate, although her main focus is on understanding the Southern Ocean's role in heat and carbon uptake and in Antarctic ice shelf melt. And she largely uses a range of climate models and high-resolution sea ice and ocean models to do her work. So Adele received her PhD from the Australian National University Research School of Earth Sciences in 2014. And then she spent 3 years as a postdoc at Princeton University, where I was lucky enough to meet her, and she became truly a lifelong friend and mentor, although she's probably happy now that we live basically halfway across the world, so I can no longer come into her office and lie on her floor and throw temper tantrums as a graduate student. So, but it's been good. It's been very good to know her. So at the end of Adele's postdoc, she took a year off to travel with her partner and her young son, who I like to refer to as Baby G, who is clear, I've just learned is no longer a baby. And in 2017, she received the prestigious Discovery Early Career Researcher Award, or DECRA Fellowship, from the Australian Research Council, and she headed back to ANU, like I said, where she is now. And so, of course, when it comes to Adele, the awards don't stop there. In 2018, she received the Myers Medal for Early Career Researchers from the Australian Meteorological and Oceanographic Society. And just in 2020, she was one of 5 scientists, both Australia and New Zealand-wide, to receive a L'Oreal UNESCO for Women in Science Award. And so in addition to all her awards, her many, many publications, I would really just like to tell you that Adele is also a stellar human being. And so now that I hope I've properly embarrassed her, I'm going to hand things over to you, Adele, and go ahead and give us your lovely talk about oceanic feedbacks around the Antarctic margins.
Thanks, Anna. Yeah, it's a pleasure to join you, and it's nice that it's a reasonable time zone here at the moment as well. You can see it's light outside. We kind of struggled a bit during the pandemic with virtual meetings and strange time zones. Okay, so what you can see here is just to give a bit of context of what I do. So on the left here is an image from satellite altimetry showing where Antarctica is changing mass over this 16 or so year period here. So you can see particularly in West Antarctica, along the West Antarctic Peninsula and Bellingshausen and Amundsen seas, it's been losing mass. And also recently you can see there's some areas in East Antarctica that may be beginning to lose mass as well. So the Totten here, the Denman Glacier here in particular. And this gives you an indication on the right of how those different areas compare when you do a whole mass budget on the ice loss. Okay. Oh, sorry. Okay. So just to give you a bit of context of how Antarctic ice melt fits into global sea level rise. So this is from the IPCC SROC report a couple of years ago. And so this is from all contributions to sea level. So this includes thermal expansion, Greenland ice melt, glacier, continental glaciers, and land use, water storage as well. And so I guess the thing to note that I'd like to point out particularly, so if you look at this inset here, which is just up until 2100. So in this high climate scenario here in the pink, the total likely range when you include all those different contributions is like something between 60 centimeters and 1.1 meters. So it's a quite a large range. And within that, if you look just at the Antarctic contribution, it's between 3 and 28 centimeters. So this is this massive uncertainty about how much of Antarctica is going to melt by the end of the century. I mean, that's an order of magnitude difference in what we think is the likely range. And so I guess a lot of that comes from the dynamics of the ice sheet instabilities that we don't really understand those instabilities and how they're going to play out. But I guess another component to that uncertainty comes from the ocean. So so the way that Antarctica is losing mass is pretty much entirely from the ocean warming. So warm ocean currents come up underneath the ice shelves and melt the ice shelves from underneath. And so you can see this figure on the left shows where the ocean has been warming around Antarctica. As you can see, it's been warming particularly in these same regions where Antarctica is losing mass. So on top, Antarctica is actually growing slightly. So there's an increase in snowfall, but that's balanced, well, overwhelmed by an increase in the melting driven by the ocean. And so I guess the motivation for my work is to understand how the ocean temperature around Antarctica will change in the future, as well as to understand what might be the mechanisms that are driving the current warming that we're seeing there now. Okay, so just to give you a bit of an overview of the basic dynamics of the ocean circulation around Antarctica. Oh, I forgot to say, please interrupt me if you have any questions, if anything doesn't make sense along the way. Okay, so this middle figure shows ocean temperature, a slice at 200 meters depth around Antarctica, taken from an ocean model. And so you can see it's mostly cold on the continental shelf around Antarctica, except for this bit in West Antarctica, which is warm. And so there's these different regimes of the dynamics around Antarctica. So I'll start off with what we call the dense regime. So it occurs in these 4 locations that I've circled here. And so dense water forms in these 4 isolated locations. And so the way dense water forms around Antarctica, there's katabatic winds that come down off the continent. This blows the sea ice away from the coast or from the edge of the ice shelves. And then we have the ocean water exposed to the atmosphere. Then we get a polynya and we lose heat from the ocean and form a lot of sea ice. And this releases brine into the ocean, which forms very salty, dense waters known as dense shelf waters. I'll try not to use too many acronyms throughout the talk, but might just be worth taking a note of those in case they slip into figures now and then. So this dense water pools up on the shelf and then overflows down the continental slope to form Antarctic bottom water in the abyss. So I guess other things to note, so there's warm water, this circumpolar deep water, which sits offshore off the continental slope. So this is primarily sourced from dense waters that are formed in the North Atlantic. And this is particularly warm and salty water. And so in terms of ice shelf melt, the thing that we're worried about or that we want to understand is how this warm water gets up onto the shelf. And because there's no continents or big topographic ridges across the slope, there's no sort of mean geostrophic way for this warm water to get up onto the continental shelf. And so instead, the transport of this warm water onto the shelf occurs via transient or spatially localized mechanisms. So I guess eddy intrusions up onto the shelf is one big mechanism for this to occur. And also localized flows within canyons is another big mechanism for this warm water to get up onto the shelf. So I guess maybe one more thing to note is this ASC. So this is the Antarctic slope current. So this flows westward around the continent like this, along the continental slope. And it flows around most of Antarctica except for this warm region here in West Antarctica. And there, the flow along the slope goes actually in the opposite direction, which is part of the Antarctic circumpolar current, which swings a bit further south in that area. Okay, so I said there's a few different dynamical regimes around Antarctica. They're sort of similar, but slightly different. So the dense one is these 4 circles. Pretty much most of the rest of this blue area that you see here is what we call a fresh regime. So that's very similar to the dense regime, except there's no dense water that's formed there. So we think there's no dense water that's formed there. In some locations, there are still polynyas, but there's too much freshwater input in these regions to actually form dense water that's dense enough to overflow. And so here, the waters on the shelf are quite light relative to the denser waters that sit offshore. And so we get these sloping isopycnals that intersect the continental slope. And by geostrophy, this drives a strong slope current westward in these regions. Okay, I guess the other thing that I haven't really noted is that, so generally around most of Antarctica, there's easterly winds. So these go westward around the continent and drive a southward Ekman transport towards Antarctica at the surface. Okay, so the final regime is this one in West Antarctica. And so in this regime, there's the warm water is able to access the continental slope. So these isopycnals are higher and flat. And so you can get transport that brings this warm water up onto the shelf. And we think the main reason that happens is because of the lack of this slope current in this region. And so instead, the Antarctic circumpolar current sweeps close to the continental slope here. And that allows this warm water to access the shelf. Okay, so I guess what I do is mostly modeling of this system and trying to understand how this system might respond if we change different types of forcing looking into the future. And so I guess some of the things to think about when we model this are that there's a lot of small scale processes that go into this dynamics. So I'll just go through a few of those so you know some of the difficulties of what it is that we're trying to model. So polynyas, so this is where the winds push the sea ice away from the coast. So you can see one here. And so these are particularly small scale. So, you know, they can be on the scale of, you know, tens of kilometers. Another thing is eddies. So I said eddies are important for bringing warm water intrusions up onto the shelf. So the Rossby radius around the continental slope and shelf is on the order of sort of a kilometre or two. And so you need quite high resolution in order to resolve that fully. Dense water overflows down the slope are particularly difficult to model. I've got another slide on that. I'll talk a bit more about that in a moment. And then also the slope current. So the continental slope is a very narrow, steep region around the continent. So just having the resolution to resolve that continental slope for a start is difficult. And then there's the dynamics of that slope current that follows that. Okay, so a little bit more about the overflows and how they are represented in models. So coarse resolution models usually struggle to produce dense water formation on the shelf. So how I described it before, you have these polynyas right up against the coast and the dense water, which then flows down the continental slope. So instead, dense waters often produce dense water through open ocean convection. This is what Hannah studied for her PhD, actually. So out here in the Weddell Sea, this is one that actually occurred in the observations, but throughout the whole observational period, there's been a 3-year record where a polynya like this has occurred. So we think that they're a very rare occurrence. However, in coarse resolution models, they actually occur much more frequently than this and for a much longer duration, which we think is unrealistic representation in the models. Okay, and so even models that can produce this dense water up on the shelf struggle to get the overflows down the continental slope. So this is what we see in observations. We see some entrainment of the warm waters into this dense water as it flows down the slope, but the dense waters still get down to the bottom of the ocean. In a coarse resolution model, your topography looks more like this, like steps going down the continental slope. And so as your dense water flows out onto the next step, you then have parameterized convective mixing. And so you can overmix your waters as you do this. And you end up with dense waters that don't make it all the way down to the abyss and end up at some intermediate layer instead. Okay, so the work I'm going to be talking about today comes from this model called Access OM201. So this is a 10th degree horizontal resolution model. It's a MOM5 ocean and size 5 sea ice. So it has 75 vertical levels in the ocean. And we force it with JRA GO-GO-DO atmospheric forcing. And there's 2 sort of base control states that I'll be talking about. One is an interannual forcing, so with 60 years of historical forcing. And we also quite commonly use what's known as a repeat year forcing experiment. And so for this, we've chosen this period, May 1990 to April 1991, and we just repeat that single year of forcing over and over again. And this creates like a really stable baseline state. And so then when we do perturbations, it's much easier to see the response if you don't have to worry about that interannual forcing variability on top of that. And so these figures here just give you an indication of the control state of the model, how it compares to observations. So it does pretty well. You get this warm region in West Antarctica and cold around the rest. In the dense water formation regions, we get high salinity. You can see in the Weddell Sea and the Ross Sea in particular, that stands out. So it does pretty well. Oh, sorry. Okay. So just another thing. So I mentioned there are these different regimes, the dynamics at different locations around Antarctica. So this is just another comparison against observations to show that we get those reasonably well as well. So this bottom, okay, so what you're seeing here, so each of these lines is a transect across the continental slope. And so across each of those transects, we've assessed the density and temperature structure against these 4 different types of regimes. So dense is where you get these dense cold waters that flow all the way down to the abyss. Warm waters, you have this connection with the warm waters. Fresh waters, we have the ice signals intersecting the slope. And so on the top is the model regimes classified by these colors here. And beneath that is based on observations from the Thompson et al. 2018 paper. And I think they compare pretty well, especially given that the observations are actually missing huge sections. Like in here, there's pretty much no observations from that section there. Okay, one more thing. So just to show that we do get this dense shelf water formation up on the shelf, and this overflows down the slope. So what this is showing here is transports. So this is summed vertically upwards across 1,000-meter isobar. So as the waters are flowing down the continental slope. And so at the very bottom in the densest layers, we have increasingly northward transport. So this is our dense water flowing down. And then above that, we have southward lighter flowing waters. This is our circumpolar deep water flowing back on, and then surface waters flowing back on top of that. And the dense waters are formed primarily in the same 4 locations as we see in the observations. And the green colors here is showing young waters right at the ocean floor. So these dense waters are reaching right down to the abyss. And you can start to see the pathways that these are exported northwards by these arrows indicated here. Okay, so I did have a movie of this, but I tested it before and I think it's going to be too slow to stream. Is that really slow?
It gives you the idea. It's about 1 frame per second or so.
Okay, yeah, maybe it depends on your internet connection where you are. But yeah, so what it's trying to show is that this is a dense water mass. This is just showing the densest water mass from the model. And so you can see these overflows. This is in the Ross Sea here, overflows coming down the continental slope. Maybe I can send the link later. It's a quite nice movie. It's on YouTube as well. Okay, so to get into the actual results. So I'm going to try and go over 3 different studies that we've done recently with this model. So the first one is looking at when we increase the freshwater input from Antarctica, how does the ocean respond? The second one is looking at interannual variability in ocean transport in ocean temperature along this section of West Antarctica here. And then thirdly, looking at how the ocean responds when we change the wind stress around Antarctica. Okay, so firstly, looking at when we add increased meltwater from Antarctica. So this has been done a lot before in coarse resolution models. And so generally what coarse resolution models show, so in the background of this little schematic here, I've got just a very simplified overturning circulation. So we can imagine we have dense water formed on the shelf and this overflows. And then we have a warm water transport above that, which returns flow back onto the shelf. And so if you imagine shutting down that overturning circulation, so the overturning, when it's happening, takes cold water down to depth and brings warm water up onto the shelf. And so if you shut down those vertical heat transports, what happens is the cold water is no longer able to descend to the abyss. And so you get a cold anomaly at the surface, and the warm water is no longer able to exit out of the surface to the atmosphere. And so you have an increased stratification and you see warming in the abyss. And so there's a whole host of coarse resolution models that have shown this response. I guess the caveat is that these coarse resolution models have this dense water formation usually, which is in open ocean polynyas, not dense water formation on the continental shelf. So I guess we want to sort of repeat this experiment and see if we actually resolve this dense water formation on the shelf. Do we see the same response or not? And one indication of what might happen comes from, so there's this idolized study by Kate Snow and others. So they had an idolized, just an Atlantic basin. And so they found when they increased the meltwater that they had, so they still have this cooling, this is Antarctica down here, cooling on top of warming. But if you look at the depth range of the cooling, it extends much further down. So typically in the coarse resolution models, the cooling is only like the top 100 meters or so, and then warming beneath that. Whereas here we're seeing cooling down to 1 kilometer or so. So basically covering the entire continental shelf. And I guess the difference between these two is quite important because it matters what temperature the ice shelves are going to see in the future, if they see warming at the grounding lines or cooling. Okay, so this study was led by Ruth Morman. So she did this as a final year undergraduate project a couple of years ago here, and she's now a grad student with Andy Thompson at Caltech. So what we did was we applied 2 freshwater perturbations. So we ran them for 10 years each. And so we took projections from an ice sheet model run by Nick Gollidge and others. And so we had freshwater projections from Antarctic ice melt for an RCP 4.5 and RCP 8.5 projections. And so I'll call these meltwater 1.5 and meltwater 2.8. So that's 1.5 times the control historical freshwater input and 2.8 times, but you can also think of them as the RCP projections as well. And so what we did was we looked at where ice shelves are currently melting over the last few decades. And so we just enhanced in those areas, but we found that it doesn't actually really matter what distribution you choose around Antarctica. There's quite a strong connectivity in the coastal current and the slope current around Antarctica. So even though we're only applying meltwater here, you'll see in a bit like we also see changes in the dense water formation in East Antarctica and the Weddell Sea as well. Okay, so the main first thing that we found was that the dense water formation slows down. So I guess that's what we were expecting. You add in fresh water and you can't form as dense water. And so this is showing the age. I guess if you're not familiar with age in ocean models, maybe I should mention that. So age is like an idolized a tracer that we put in models. So it's set to set to 0 at the surface. And then as waters move away from the surface, it just increases at a rate of 1 year per year. So where waters have an old age, that means they haven't been in contact with the surface for a long time. And where the age is 0, that means that they've recently been in contact with the surface, with the atmosphere. Okay, so these are the 2 different meltwater experiments. And so this is showing the age at the bottom of the ocean. And so you can see this pink around here at the bottom of the ocean. So that means that the waters that were descending down that had recently been convecting on the shelf and then overflowing down the continental slope, those waters are not as young as they used to be. So those are aging. So that means our convection, our dense water overflows are slowing down. Okay, I guess you can see one thing to note between the 2 different experiments. You can see that there's, like I said, it's not the same sign of the change between the 2 experiments. So, and we think that's due to how quickly the dense water formation is shutting down in different regions. So in the Ross Sea here, we see aging waters in both experiments. And if up on the top left here, this is showing the mixed layer depth anomaly in these experiments. So shallowing mixed layer depths imply that the convection is shutting down quite quickly. And so in the Ross Sea, the dense water formation shuts down quite quickly. And so we're no longer convecting surface and bottom waters, mixing those on the shelf. And so those bottom waters on the shelf age in those regions. You can see in the Adele land dense water here, we actually see a difference. So in this one here, it's still still green, so not aging yet, but it starts to go pink in the higher meltwater experiment, so it ages more there. So it's kind of a threshold thing. As you increase the meltwater, you start to shut down different regions. But in some of the other dense water regions, so particularly downstream of the Weddell Sea, and also there's convection, there's a dense water formation site here near Pritz Bay, and downstream of that you can see green here. And so I think what's happening there is that you can see there's not a strong decrease in the mixed layer depth in these regions. And so I think convection there is slowing, but not shutting down completely. So you're still convecting, but you're not forming as dense waters to escape off the shelf. And so you still have young waters on the shelf that you're convecting, but instead of overflowing down the slope, those waters are instead preferentially staying on the continental shelf and moving downstream. And so particularly downstream of the Weddell Sea in this West Antarctic region, you can see a lot of green here. And so the dense water formation in the Weddell Sea is still continuing, but perhaps just not forming as dense waters as before. And so those young waters are staying on the shelf and continuing around. Okay, so one other big change we see in the dynamics when we add this fresh water is a change in the Antarctic slope current. So this is the anomaly in the speed in the upper 500 meters in the two different perturbation simulations. And so you can see the red starting to form around here on the slope and intensifying a lot here. And so this increasingly isolates the shelf region from the open ocean region and is going to reduce the transports of waters between those two regions. You can also see this in a transect. So this is one transect just taken here on the Adele coast. So this is what it looks like in the control simulation. The background colors here are the salinity and the change in salinity. So you can see a large freshening on the shelf in the perturbation experiments. And because that slope current intensifies a lot and isolates the shelf, that freshening is really stays on the shelf. Like we see very little change out in the open ocean here. And increasingly, you can see these isopycnals, which used to slope upwards in this region, are now intersecting the slope here, which is consistent with the increase in the slope current we see around there as well. Okay, so what does all this mean for the temperature change, which I guess is what we really care about for understanding ice melt in the future, the feedbacks from the ocean. So we see quite regionally varying temperature changes and also temporally, I guess if you think about that we might start having a small melt, and then as we go further into future, we'll get an increased melt. You can kind of think of this as a temporal progression between these two. So you can see there's some regions here that are cooling that then start to warm once you add more meltwater. So I guess one very clear signal is this warming offshore. So this is not on the continental shelf, this is further away from Antarctica. And so this is linked to that isolation of the shelf. So it used to be that we used to have warm water transport up onto the continental shelf. But as you increasingly isolate the continental shelf, those warm waters stay offshore and can no longer get onto the shelf. And so you warm the waters just off the slope. So another thing to point out is, so we're in the same regions where we saw that convection was completely shutting down. So here in the Ross Sea in both simulations and in East Antarctica, just in the larger melt simulation, we see warming there. So that's where convection is completely shutting down. So we're getting this stratification effect with cooling above the warming. However, in these regions where the convection slows but continues, we're actually seeing cooling. And so that's because we're still convecting, so we're still cooling from the atmosphere, but those cold waters are no longer being exported down to the bottom of the ocean. Those cold waters are now preferentially staying on the continental shelf and being advected around the continental shelf downstream from the dense water formation sites. And so we can summarize this here. So if we go back to these two mechanisms that we talked about earlier, so I guess we find that these are both occurring. So I guess it's a temporal progression from one to the other. So as the dense water formation starts to slow down, we get a cooling that covers the entire continental shelf in the regions where the dense water formation is still slowing. And then in the regions where dense water formation has completely shut down, and downstream from those regions as well, we do see this warming on the bottom of the continental shelf. Yeah, so I guess it's a complex response, more complex than what we've seen from just the coarse resolution models. Okay, so leading into the next study. So one thing that we saw in this study, so in this West Antarctic region, we saw this strong cooling, which I've kind of mentioned we think comes from the Weddell Sea. And so you can see that here, if you look, this is a progression throughout that meltwater simulation. You can see this cold anomaly starts up here at the tip of the peninsula and then progressively intrudes throughout most of West Antarctica. And so I guess we were quite interested in this because West Antarctica is a region, hang on, I have another slide here that shows this. So West Antarctica at the moment is warming and quite a lot in the ocean and melting, contributing to sea level rise as well. So I guess this is more this is the sort of the eastern part of West Antarctica and the western part of this Antarctic peninsula that we're seeing here. So these red dots show the glacier change over this period. And each of these dots is a single glacier. I think there's like 600 or something of them in this region. And pretty much all of them, at least in the southern part here, have been losing mass. Right, so we wanted to understand this a bit more. So I guess, yeah, I've mentioned this connection from the Weddell Sea, but the thing is, if you look at observations, this connection from the Weddell Sea, there's not a lot of evidence for it. There are pretty sparse observations in this region, which may explain it. So it's been observed that there's connectivity around this tip of the peninsula here. And then, so I think the dashed lines here is where there's kind of inferred observations that there might be a current there, and solid lines is where there's like an actual velocity measurement of currents in those regions. And so there's, yeah, kind of sparse measurements here, but this region here, it's not really clear that this current here connects up with this one here at all. So it's hard to say from observations how much connectivity there is there, and it hasn't really been studied much before. So what we did with the model was to do some perturbations, just focusing in on the on the Weddell Sea in this case. So the red here is showing where the dense water is formed in the Weddell Sea. The green shows the age at the bottom again, so showing where the dense water overflows down this western side of the Weddell Sea and then goes north to the Atlantic primarily through this pathway. And so in this simulation, we just altered the freshwater input coming from Antarctica along this blue line here. And we did 2 perturbations for 12 years each, reducing this runoff by half and then doubling it as well. So firstly, just to look in the control state. So we've added a passive tracer, so just like a dye tracer to track connectivity. So we've set the passive tracer to 1 at the surface in this region here, and then just look where that passive tracer goes. I think this is at the end of year 12. So what I'm showing here is, so this black solid line is the 1,000 meter isobath. And so north of that, the passive tracer is shown at the ocean floor. So that's to trace the bottom waters going northwards. But on the continental shelf, I'm showing the passive tracer at 200 meters depth. And so you can see that there's this strong connectivity all around this coastal current of West Antarctica from the Weddell Sea. And so then the question is, when we change the dense water formation in the Weddell Sea, how does this connectivity change and what impact does that have on West Antarctica? Okay, so these are our 2 perturbations. So in the left one, we increase the dense water. So you can see the passive tracer export in the abyss. This red here is increasing. So we're getting more dense water overflowing. And then when we decrease the dense water, we get the opposite. We get less dense water flowing northwards here. But the quite surprising thing is that the connectivity around to West Antarctica is exactly opposite to that. So I sort of hinted at this before. This was actually quite a surprising result when we found this. So I guess what it's implying is that when you increase dense water, your dense waters that start off here are flowing down the shelf, and you're getting less of those waters traveling around to the west. And then when your overflows decrease, I guess that water instead travels around the continental shelf to West Antarctica. And this is a really big change. So if we take a transect here and look at how much passive tracer is reaching this transect on the West Antarctic Peninsula, this is the control, and this is the increase and decrease dense water experiment. So sort of, by a factor of 2 or so, we're changing the connectivity between these regions. So it's pretty large changes. Okay, so then what impact does this have on the temperature? And so similar to what we found in that whole circumpolar freshwater perturbation experiment, so when we add fresh water into the Weddell Sea, we decrease how much dense water is being exported. And so instead we increase the connectivity around here. We find we get cooling on the West Antarctic Peninsula. And so this is because we have cold waters in the Weddell Sea, and these cold waters that have recently been convecting and losing heat to the atmosphere are now increase their advection around here. And so we see cooling on the West Antarctic Peninsula. And the depth range of this sits at about the same depth that the ice shelves terminate, the grounding lines the ice shelves terminate in along this section as well. Okay, so this is the same figure before, just showing the cooling. So now looking at a transect here, this plot here is showing the changes in temperature and salinity in both experiments. And so this blue one here that you're seeing is when we decrease the dense water, so that's this dashed blue line here. And so when we get cold waters coming from the Weddell Sea, these waters are also fresh. So we get a cold and fresh anomaly together. And then the opposite experiment, when we have decreased amount of waters coming from the Weddell Sea, we get warming and salinification. And so we can summarize this mechanism here. So these are the 2 cases. So when we have strong dense water export from the Weddell Sea, we have less of a connection around. And so instead, the waters on the West Antarctic Peninsula are dominated by intrusions, local intrusions across the slope of warm and salty circumpolar deep water. And so we get warming and salinification. And when we have decreased bottom water export from the Weddell Sea, then we have increased connectivity of these cold, fresh and light waters, and we see cooling and freshening on the West Antarctic Peninsula. And so I guess the implication for this in the future is that if Weddell Sea dense water slows down in the future, this may actually be a negative feedback along the West Antarctic Peninsula coast, which is a hopeful thing. It also has implications for model biases on the shelf. So I guess a lot of people are focused on getting dense water formation right on the shelf in order to get the bottom water in the abyss right. But I guess what this is showing is that if you get your dense water formation on the shelf a bit too high or a bit too low, it's also going to have big implications for temperature downstream on the shelf as well. Okay, so just out of interest, we had a look. So we also have this interannual force simulation I mentioned. I haven't actually shown anything from that yet. So we just wanted to see if this mechanism appears in that simulation as well. So this is just comparing the control of the model to observations. There's amazing seal data in this area. So I've been looking at the ship data. So ship data, there's like 100 or something profiles, over 40 years in this region, but seal profiles, there's 40,000. It's incredible. And so the model does quite well, getting these warm intrusions in the canyons across the shelf slope, as well as you can start to see this cool signal along the coast where the slope current flows down there. Okay, and so this is now showing the variability from this interannual force simulation. So the blue line here is the temperature in this region, the West Antarctic Peninsula. And this is detrended, so this is warming in this model simulation, similar to the observations. So what I'm focusing on here is the variability. So we've removed that warming trend. And then in the orange, we're showing the variation in the dense water formation rates in the Weddell Sea. And so the dense water formation we've averaged over the preceding 4 years because there's a time lag for those waters to advect around, and there's some sort of pooling and memory of those as they sit on the shelf here before they flow around as well. And so I find this incredible how well this matches up. So I'm currently trying to go through all those ship observations and see if we can come up with anything from observations going back in time that might show us what the actual variability in the ocean was, temperature variability in the ocean. There's not any observations of dense water formation rates, but we can maybe hope to see what the variability in temperature is going back in time. Yeah. Okay. So sorry, I'm realizing I'm trying to get through a lot here. So let's go on to the last study. that I wanted to talk about. So the last study is looking at winds around Antarctica and how the ocean circulation might change in response to those winds. So just to give some background about what we know about the winds at the moment. So I guess most people focus on these easterly winds. That's what's shown in the red here. But actually, if you look at the meridional winds, those are nearly as large as the easterly winds. And then if we look at trends, so this is some analysis done by Julia Neem, who's a grad student at UNSW. And so she's looked at a bunch of different reanalysis products. That's what's in the red. And so this is averaged over the region, this red region here, so where there are easterlies around Antarctica, and then averaged across, I guess it's averaged across all longitudes and latitudes within that red region. And so there's a lot of variability in the reanalysis, and it's hard to say what the trend is. Maybe there's a decrease in this meridional wind speed. And then if you look at a CMIP6 projection, so they generally show a decrease in both the zonal and meridional winds, but you can see that the grey shows the spread in there. There's a large spread of those trends. So I think it's still very uncertain what's actually going to happen there. Okay, so this project, we actually did this, it's been quite fun. So I guess I was thinking about this a few months ago and found that, I find that even at my stage of my career, I still often do projects on my own. I, do all the analysis, come up with ideas, discuss results and interpretation with people. But I was kind of wondering, maybe it'd be fun to do a more collaborative project. And so this is exactly what we've done here. So I ran some simulations, and then we've been doing all of the analysis on GitHub, and we do it mostly in hackathons. So we meet once a fortnight, this team of people you can see here, and we discuss results we've got so far, and we sort of allocate different task analysis to people, and we all split it up. We have a different person convening each time, so we're trying to make it so that no one person in particular is leading it. And it's been a lot of fun. I would definitely recommend trying to do projects like this if you haven't tried it before. Yeah, I think it's great as well for students and postdocs to be involved. I think they've learned a lot, seeing how to develop and progress through projects. Okay, so what do we expect when we change the winds based on past studies? So there's been a few studies done on this before. So one of the main mechanisms that we might expect, so this is just looking at an easterlies increase. So there actually haven't been any past experiments looking at meridional wind changes. So we're going to look at both, but from just an easterlies perspective. So if we increase the easterlies around Antarctica, we find that the Ekman transport southwards increases as expected. So this will increase your SSH around Antarctica, and it also depresses the isopignal. So you're bringing in those surface waters and pushing everything else down. And so the colors here are showing your background temperature gradient in this region. So you generally have colder waters near the surface and warm waters deeper in the ocean. And so if you're pushing your isopignals down in depth space, that's gonna appear as cooling on the shelf and warming in the abyss. So this is kind of what we expected when we started this project. Okay, so what we've done is to change both the zonal and meridional components. And so we've just done given that it's kind of uncertain what's happening in the future with the winds, we've just done a simple 10% increase and 10% decrease simulation. And we've changed these south of this blue line, which matches up with, if you look at the zonal winds, where they switch from being westerlies over the Southern Ocean to easterlies around Antarctica. Okay, so I guess the first thing we looked at was SSH, because we thought this would be a clear result. So as we increase the easterlies, we get this Ekman transport increasing and increase SSH. And so if you look at this wind plus experiments, this is where we increase the winds by 10%. This is a time series along here. So initially, in the first couple of years, we do see a positive SSH anomaly, but this is pretty rapidly overwhelmed by a declining SSH, which we were very confused about when we first saw. And so I guess what's happening as well is that we're getting an increase in the dense water export. So we're getting more of our dense waters formed and flowing off the shelf. And so this change in the dense water explains what we're seeing with the SSH here. So if we go back to our little schematic of our overturning, the dense waters carry cold, fresh waters off the shelf, and the warm return waters bring warm, salty waters back on. And so if you increase this overturning, you end up bringing more salty waters onto the shelf, which through a steric contribution decreases your sea level over the shelf. So generally, salinity always wins over temperature around Antarctica in terms of setting the density. Okay, so if we then look at age, again at the bottom, so we have associated with that increase in that lower overturning circulation, we're getting younger waters at the bottom, so we're exporting more young dense waters down to the abyss, and the opposite in the decreased wind experiment. And the salinity is, as I mentioned before, so as you're bringing more warm waters onto the shelf, as you increase that overturning, you get more salty waters on the shelf, particularly in these regions where you're forming the dense water. Okay, so I guess the question then is, why does this dense water increase? I guess this is not something that we were directly expecting when we increased the winds. So we came up with 3 possible mechanisms. So the first one is that if you have outcropping isopycnals, and as you increase the gradient in your winds, you might increase the Ekman upwelling coming up along those isopycnals. And then once you increase your upwelling, you're then going to increase your heat release and your whole overturning circulation. The second was that we thought as we increase the winds, because we've just amplified the spatial pattern in the control, that we're also amplifying these like localized katabatic-like winds that drive these local polynyas and local dense water formations. So we thought that might be what's happening. And then thirdly, we thought maybe there could be a sea ice effect, that as we change the winds, we're changing our export of sea ice northwards, which would mean there's less sea ice over the shelf. And so then you have more open water and you can form more sea ice. And this leads to a feedback where you have saltier waters on the shelf and more dense water formation. So the first one I won't go into in detail, just to say that we found that these isopycnals don't really outcrop. So a lot of this transformation happens very far south or even beneath the surface. And so these isopycnals aren't really experiencing much direct wind forcing. So the second one, this idea of that it's just these local winds in the dense water formation regions that we're enhancing and moving more sea ice away from the coast and enhancing the polynyas. So we tested this by doing another perturbation experiment. So you can see there's 4 little yellow regions here. So we did the same wind increase experiment. We just didn't change the wind in these 4 little yellow regions. But we found that that had nearly no effect. So the blue is the original wind experiment. The orange is when we don't apply the winds. We apply the winds everywhere except in these little yellow regions. And there's not much of a change between the orange and blue bars in the 4 dense water formation regions. So yeah, we were surprised by that as well. So that leads us, so the overturning still increases even when we don't apply winds in those regions. So that leaves us with the sea ice mechanism. And so, okay, this is showing in the increase and decrease wind experiments. The colors are showing the change in the thickness. So when we increase the winds, we have less sea ice over the shelf. And the arrows are showing the change in the ice velocity. So generally in the wind increase experiment, you can see there's ice being moved offshore out into the open ocean. So we're moving sea ice away from Antarctica, which means that we then have less sea ice thickness over the shelf. And so when there's less sea ice thickness, you then have more ocean exposed to the atmosphere. And so then you can actually form more sea ice. So confusingly in this left one, the sea ice formation actually increases, but you're just moving it away much faster than you're increasing the formation of it. And so as you increase that formation of the ice, you have an increase salinity, and then you can increase your dense water formation. And so you can see that it's primarily the northward motion of the sea ice here that's moving that sea ice away. And if you look at the wind stress on the sea ice, it's nearly aligned with that as well. So it's coming from the northerly component of the wind. There's not much rotation between the wind and the sea ice motion. So we did another couple of experiments to test that. So we did our wind increase experiment, but we separated it into a zonal only and a meridional only wind change. And so the idea here was that it should come from the meridional winds driving the sea ice northward, not from the zonal wind. Okay, so just to remind you what we saw before, this is identical to what we saw before. So we had that initial increase in SSH, which we thought should come from the easterlies, from the zonal component, driving this Ekman transport and southward and increasing SSH. And then we think this bit here should come from our dense water increase, which comes from the meridional component. So if we look at our two new experiments, this is exactly what we see. So the green here is the zonal only. So this is increasing Ekman transport, and we get a SSH increase over the shelf. And when we just apply the meridional component of the winds, we don't see any of that initial SSH increase, and we get a decrease in our SSH as we bring more salt onto the shelf as we increase the overturning. And that's consistent with, if we look at the dense water change comes entirely from the meridional component. If you change the zonal winds, you get no change in the dense water formation. Okay, just have a couple more slides to go. So just finally looking at the temperature impact, which is what we care about for our ice feedbacks. We're in those wind experiments. So this is wind increase and wind decrease. So off the shelf in the abyss, there's cooling. So that's because we're exporting more cold dense waters into the abyss. Here we're seeing, if you look downstream of where the dense water formation sites are, we're actually seeing warming in these sites. This is because we're bringing more warm waters onto the shelf as we enhance that overturning. But there's also cooling in other regions here. And so again, this makes more sense if we split it up into our zonal and meridional components. So this is the temperature change just from the zonal component and just from the meridional component. And so here I've got two schematics showing what's going on. So this one showing the easterlies, this is similar to what we've seen before. So we increase the easterlies, we depress our isopycnals on the shelf, and this causes cooling. And so you can see nearly all the way around the shelf in the zonal experiment, you're seeing cooling there. And then this is when we just increase the meridional winds, which are primarily northerlies around Antarctica. And so we export more sea ice northwards, which then decreases the sea ice concentration on the shelf, which allows us to actually form more sea ice, but that's exported faster than it was before. And so this increases the salinity on the shelf, which allows the dense water to increase, and the overturning increases, which brings more heat and salt onto the shelf. And so you can see there's warming, particularly enhanced at and downstream of the dense water locations. Okay, so then just to summarize, sorry, there was a lot in there. Yes, I think the main takeaway messages are, so when we do these different experiments, the sign of the thermal feedback, so the sign of the temperature change is complex. So it varies regionally, even if you apply like circumpolarly uniform forcing changes, because of the different dynamics around Antarctica, the temperature response varies regionally, and it's also likely to vary temporally. As you go from just starting to slow down the overturning, you get one sign, and then as you completely shut down the overturning, you get a different sign of your temperature response. And I think we've shown that so accurately simulating dense shelf water formation actually on the shelf, not just in open ocean polynyas like most coarse resolution models do, is really important to get this temperature response and the temporal progression of this temperature response correct. I guess the other thing to note, if you look at the meltwater perturbations compared to the wind perturbations, like they're not entirely accurate magnitude compared to what we might think for future projections, but the magnitude of the temperature change for the meltwater is like an order of magnitude bigger than for the wind changes. So it's likely that the meltwater response will dominate whatever happens around Antarctica in the ocean in the future. And it would be great if we could have more certainty on how the atmospheric forcing is going to change and how the melt coming off Antarctica is going to change, so we can do like more projection-like experiments rather than just these idealized perturbation runs. And then finally, future directions. So there's a lot of things that this model does great, like the dense water formation, but there's a lot of things that are lacking that we're currently improving as well. So we're currently developing a higher resolution model, 1/20th degree, At the moment in this model, the freshwater from Antarctica is actually put in at the surface, which is not ideal because when it melts from ice shelves, it actually goes in more like hundreds to 1,000 meters at depth. So we're working on inputting that at depth as well. We'd also like to add tides, and we're improving the model coordinate. So we're moving towards MOM6, where we can have a hybrid vertical coordinate with less mixing of the overflows. And we're also working on incorporating ice shelf cavities, so we can get that circulation within ice shelf cavities and the melt going in the right places, and interactive parameterizations of melt with changing ocean temperatures as well. Cool, that's me done. Sorry, it was a bit longer.
Yeah. Awesome. Thank you, Adele. That was excellent. I think we'll open it up for questions now. Just take a few minutes to go ahead and do that. So I think people are allowed to go ahead and unmute themselves. If not, you can put your question in the chat and I can read it for you as well. So first things first, though, do any of our graduate students have questions? All right. If you come up with some, I will totally let you go. Otherwise, it looks like Till wants to go forth. So go ahead, Till.
Maybe I can break the ice, metaphorically speaking, for the grad students.
Why?
Thank you, Adele. That was a wonderful talk. Really enjoyed it. I was just wondering, because you showed so convincingly how important the sea ice is in the wind perturbation runs, yep. And you presumably have important impacts on sea ice formation and dense water implications when you have the freshwater perturbations as well. So I just wanted to ask whether you could comment on sea ice effects for your first set of runs.
Yes, good question. So I think the sea ice, I can't remember the exact regional details. I think, again, there's some regional variability in the sea ice change in the melt runs. But generally it follows the sea surface temperature change. And so as you get your overturning slowdown, you generally see cooling at the surface over warming below. And so that cooling at the surface, you see some areas where you increase the sea ice due to that cooling at the surface because you're not melting it as fast. I think that was the main change.
And yep. So do you see feedbacks then, if you have increased sea ice formation, that brine rejection, etc., might negatively feedback and drive some deep water formation in that regard?
No, I guess the winds are still similar in that experiment. So if the dense water is formed in those localized polynyas, we're still pushing sea ice away from the coast, and so we still have dense water formation where there's winds. If it's able to, like, as long as there's not too much freshwater input that overwhelms that dense water formation. Yeah, probably I can pull up that sea ice figure for you tomorrow when we chat.
Great. Yeah, thank you.
About that more. Yeah.
All right, anybody else?
I had a quick question.
Go ahead, Evan.
Hey, Adele, great talk.
Hey.
My question, so you talked about how the northerly winds, or the northern winds are pushing sea ice away, and that's causing the sea surface height to lower. And I was wondering, so you have Ekman transport pushing seawater towards the pole, and so you're going to have a counteracting, so the winds are pushing the ice north, and the water, like the current, is pushing the ice south. And it seems like the greater forcing is the northerly winds, but I was wondering, like, how much of a dampening effect does the Ekman transport have? Like what is the force back towards the south versus that northerly force?
Yeah, so I guess you can see that in the so if you look at this wind, so I guess the wind plus perturbation here has both the zonal and meridional. So I guess there's two different timescales that these things act on as well. So the easterlies, which piles water up on the shelf, that's Ekman transport, so it responds really fast. And so, within the first month of the experiment, you can see that the SSH starts to increase there. Whereas the timescale for the dense water to increase, I guess there's a feedback there that it takes a while for the sea ice to go off and for the salinity to increase, and then for the whole overturning circulation to increase and bring on more salinity onto the shelf. So you can see that takes something like 5 years for that to spin up. So I guess overall, the meridional component wins in the long run. So you can see the experiment where you have both the meridional components dominating, but there's two different timescales. So if you look in the first couple of years, then the easterly zonal component wins on those shorter timescales.
Gotcha. So there's almost like a maximum of positive SSH response to just the Ekman transport, because you quickly go up to that 5 centimeters and then you kind of stay flat the whole time.
Yes. Why is that? Yeah, I guess you can't keep building your SSH up indefinitely. At some stage, I guess it will go unstable, or there'll be currents to stop that, keep going on forever.
Cool.
Yeah,
thanks.
No worries.
All right.
I'll ask a
Liz?
question.
Go ahead, Liz.
My room that's turning yellow. So something that in that video, and there's a lot of what I noticed throughout your talk, was just how important all of these small scale features are. And that with this simulation, you can start to get at some of that. But I was wondering what your thought on is the bigger challenge, getting these fine scale features correct, or having any kind of observational benchmark to constrain what the models are telling us.
Both. I mean, more observations and super high resolution models would be awesome. And I guess people are advancing on both fronts as well. I mean, I guess around Antarctica at the moment, like observations are so sparse, like particularly in winter. So I mean, ships only go in summer. Like the Argo floats don't really get up onto the shelf. So yeah, pretty much like the only winter observations we have are from the seals. So I think, more seal data going forward, or moorings. I guess moorings are fantastic. But again, they're so expensive and so limited. And the other thing with moorings on the shelf as well is that like the icebergs tend to take them out. And so like you normally can't get the top like 300 or 500 meters of the water column, because it's too dangerous for icebergs coming through that you'll lose them. So they're kind of okay for on the slope, measuring dense water or something at the bottom, but you can't see what's happening at the surface. So observations would be fantastic, but I think it's pretty limited, what can actually be done physically there. It's a pretty challenging environment. So I think there's a lot of scope for modeling to fill in those gaps and to advance our understanding, given that it's even unlikely in the future that we're going to increase observations by all that much, I think, looking forward.
Cool, thanks. And by the way, that zonal meridional wind experiment, that is so clean, those results. That is
I know. It's
so
really
cool.
nice. Yeah, it's good. Really good. No worries. Yeah.
Cool. I do have a question if nobody else does.
Lee Orff posted in the chat. He was
Yeah.
wondering if you could paste a link to that animation in the chat.
Oh yeah. Okay.
Yeah,
Thanks.
so you can go ahead and do that. Adele, I'll ask my question. So in Ruth's, I think this was in Ruth's results, where you're kind of looking at the increase in speed of the Antarctic slope current. There was a part where you have this major decrease on the west side of the Antarctic Peninsula, or at least what it looked like in comparison. So you've got this increase kind of all around coming through the Weddell Sea, and then kind of around the tip, then you end up having a decrease. And I was wondering, what is the cause of that? Is that like ACC impinging on the shelf there, or kind of?
Hang on, sorry. I was half trying to look at that.
Yeah, no, I know. That's why I was
okay,
like,
so Let me pull up the figure.
Yeah. So especially in the meltwater 2.81, you've got all this upper 500 meter speed, especially around on the western side of West Antarctica. What drives the speed decrease there?
Here.
Yeah.
Right. Okay. Yeah.
No, I'm not sure either. That's why I was like, is this an ACC or?
Yeah, it's definitely the ACC. That is what you're seeing there. So you get like the most southerly jets and fronts of the ACC that come right up against the continental slope there.
Yeah.
I guess you're changing. I guess when you add meltwater, I guess some of that meltwater, particularly in that region, is maybe not going to be tied to the shelf. So it's going to be escaping out to the open ocean, and you'll be changing your whole stratification in the Southern Ocean as well.
Yeah. Cool.
Not a very good answer.
No, that's all right. I'm thinking about that too. I'm curious about it anyway. I think.
Okay. This is your
This is
your family room.
Okay.
The link is coming. Sounds like. Okay. All right. If no one else has any other questions, I think we should just thank Adele one more time. And if you have meetings, those will be tomorrow. Okay. Yes, if I remember, because we have lots of different things. Too many different time zones here. But otherwise, let's give Adele another round of applause because that was super cool. I'm excited again to think about Antarctica again. I miss it.
Thanks, everyone. Yeah.
So thank you, everyone. All right.
Thanks, Adele. Thanks also for posting that link. Lee was happy about that.
Yes, Lee likes his fun simulations.
Yeah, he makes some pretty awesome tornado videos. So he was
cool. Yeah, this is made by, we've got visualization people at our local supercomputer. So it's by their team.
Super helpful.
Yeah, it's great.
So,
all right. Well, thanks again.
Oh, my stupid.
Cool. Thanks, everyone.
I hope that's recorded still. It is good.
See you tomorrow. This is so cool.
Adele, we'll talk to you tomorrow. I have a lot of things I want to talk to you about in terms of that simulation.